Hello, welcome to Econometrics Melody. In this video, we will discuss about the change in some of the square of error when a variable is added to the regression model. So first of all, we have this regression model where the independent variables are represented by matrix X and the residual term is given by this A. And to this model, we are going to add another independent variable, a single variable Z, and the residual term is given by U. Now we want to develop a relationship between the sum of the square of the error for this model with the sum of the square of the error for this model. Here we have simply added a single variable in the second model, therefore the value of X in both of the model are same and their beta coefficients are different because of the addition of a variable in the second model. Is the residual term is different. Here this M is the residual maker matrix when we regress a variable with matrix X. So in both the model, let us pre-multiply with this M. So when we regress y on x, so this is our residual term, so we write it as E. This is equal to, when we regress the x with x, the beta coefficient is 1 and therefore the residual term is 0 plus, and when we regress the error term with x is x and the error term, they are orthogonal, so the beta coefficient is 0, therefore the residual term should be this entire independent variable. And here my, let us write it as y asterisk because we have partial out the effect of x from y, so this is equal to E. Y asterisk is equal to E or E is equal to y asterisk, they are one and the same. So what we are saying is that we have partial out the effect of x. Similarly, from this y we have partial out the effect of this x. It is given as y asterisk, or this is equal to this error term, actually this residual term. And when we regress the x with x, here M, it contains x and both of these two x, they are one and the same. So if we regress it, there is no residual, so this is equal to 0, and we are partitioning out the effect of x from Z, so this is written as Z asterisk C plus, and as this x and U, they are orthogonal, therefore when we regress this U with x, then the residual term is this U itself. And let us substitute the value of y asterisk is E in this relationship, so this is equal to, and in the second model as well, x and z, these are the independent variables, so they must be orthogonal with u, so we can write it as this is orthogonal with u as well as z is also orthogonal with u. So when we partial out the effect of x from z, so this is still orthogonal with this residual term u because the z is orthogonal with u. As they are orthogonal, if we square it both the sides, we make use of Pythagoras theorem because here z is orthogonal with u. The sum of the square, so let us take the transpose of E, so this is equal to h square is equal to p square plus b square. So let us take the square of this, is c is scalar, so this is equal to c square z asterisk transpose z asterisk plus u transpose u. So this is the relationship that we get. Here is z and u, they are the vectors, so z transpose z asterisk transpose z, so this should be positive, and u transpose u, this is also positive because they are the sum of the square. So according to this relationship, E transpose E is greater than u transpose u, meaning thereby the sum of the square of the error in the first model, this is greater than the sum of the square of the error in the second model. And if we add an independent variable in a model, the explanatory power of the combined independent variables, it increases. That is why the sum of the square of the residual, it decreases. This is the logic. Now from the partition regression equation, we can calculate the value of C. So this C is actually equal to, and as C is scalar, we can write it as, this is equivalent to the covariance of x and y divided by the variance of x. So this is how we can calculate the beta estimate for the single independent variable. So first of all, let us call it as our relation 1. And to this equation, first if we replace the value of C as this, then we will get it as its square. Let me square this and write the value of z asterisk j 2 times. Now this is equal to c square into, and we have, and this it cancels out, so we are left with simply And from the partial correlation coefficient, the covariance between y and z after partialing out the effect of x divided by the square root of the variance of z and variance of y. And once we square it, so we multiply the numerator term 2 times and we remove the square in the denominator. So this is the square of the partial correlation between y and z, and we have estimated c from the partition regression equation, and this is equal to z asterisk transpose y asterisk divided by z asterisk transpose z asterisk. This is equivalent to the covariance of yz divided by the variance of z once we partial out the effect of other independent variable. So the covariance of yz after partialing out the effect divided by the variance of z, so this is equal to c. And to this term again, if we multiply and divide by z asterisk transpose z asterisk, then again z asterisk transpose y divided by z asterisk transpose z asterisk, this is again equal to another c. So this is equal to c square z asterisk transpose z asterisk divided by y asterisk transpose y asterisk. And if we cross multiply, finally we get this result. So in place of c square z asterisk transpose z asterisk in equation 1, let us substitute it by this value. Actually y asterisk, this is equal to my. We have partial out the effect of x from y, and our first model y is equal to xb plus e. So once we partial out the effect of x from y, we are left with e only. So y asterisk, this is equal to e for this case, and we have already derived it over here. So let us substitute the value of y asterisk with e, and we get another relationship. And from this result, if we take E transpose E common, then we are left with E transpose E 1 minus, and this is equal to U transpose U. Let me write it properly once again. So the sum of the square of the residual after adding a variable, this is actually less than the sum of the square of the error before adding a variable. And when we add the variable, the sum of the square of the residual, it decreases by this term or it decreases by this term, and they are one and the same. So let me write the term by which the sum of the square of the error decreases after adding an independent variable in the model. In other words, this term in the extreme right, they are equal, they are one and the same. So this is it for this tutorial. Thank you very much for your time. Thank you very much. Econometrics Matter Day.